Welcome, everyone. Today we're digging into a really interesting paper called Running VLAs at Real-Time Speed. The core idea, the mission really, was pretty bold. Get these huge vision language action models, specifically the zero policy, running fast enough for, actual real-time robot control, dynamic stuff.
Yeah, and that's been the bottleneck, right? These VLAs, they usually take hundreds of milliseconds just for one inference pass. Way too slow if you need a robot to react quickly, like catching something.
Exactly. But the big news here is they actually did it. They got this multi-view VLA running at a steady 30 hertz frame rate.
And even pushed the trajectory frequency, the sort of faster control loop, up to an incredible 480 hertz.
All in a single consumer GPU, an NVIDIA RTX 4090.
Right. And it wasn't some magic new model architecture. It was hardcore engineering. The whole bag of strategies, as they put it, focused on killing inference overheads.
So low-level stuff.
Totally. Things like using CUDA graphs to get the CPU out of the way, simplifying the computation graph itself through operator fusion, and really deep kernel optimization with Triton. Just tuning everything.
And they proved it worked in the real world. They set up this task, grasping a falling pen, which is surprisingly hard, and the optimized policy hit a 100% success rate. The end-to-end reaction time was under 200 milliseconds.
Which is basically human-level reaction time for a massive AI model. It's pretty wild.
To put a number on the inference speed itself, for 2 camera views, they got it down to 27.3 milliseconds.
Yeah, which blows the kind of official OpenPy baseline of 53.7 milliseconds out of the water.
That's a huge leap. Okay, so that's the headline. Let's back up a bit. Why is this latency, these hundreds of milliseconds we started with, such a showstopper for robotics?
Well, it really comes down to physics, doesn't it? When you've got a model with billions of parameters, pushing all that data through, doing all the math, it just takes time. And for a robot in the real world, especially doing something dynamic, if your brain takes 150 milliseconds to process what it sees.
The world has already changed by the time it reacts.
Exactly. It's always acting on stale information. You literally cannot catch a fast-moving object if your perception action loop is that slow. You're doomed to fail.
And you mentioned they were aiming for that 30 hertz rate, which means hitting a 33 millisecond threshold. Why is that specific number so critical?
Yeah, the 33 milliseconds, that's simply 1 divided by 30. It's the time budget per frame if you want to process a standard 30 frames per second video stream.
So if you're faster than 33 middles,
you can process every single frame coming from the camera. No dropped frames. Continuous vision.
But if you're even slightly slower, say 34 milliseconds,
then you have to start dropping frames.
Yeah.
You just can't keep up. And the moment you drop a frame, especially if something critical happens in that missed frame,
your effective latency suddenly jumps way up.
Right. By a whole frame time, potentially. It breaks a real-time guarantee.
Yeah.
So staying under 33 milliseconds is fundamental for smooth, continuous visual control.
Okay, makes sense. So to understand the optimization challenge, let's quickly touch on the model they were wrestling with. This zero VLA. What's its structure like?
It's a pretty hefty model, built in 2 main parts. First, there's the VLM, the vision language model. That's the big one.
Doing the seeing and understanding.
Exactly. It's based on PallaGemma. Comes out to around 3 billion parameters total. You've got a SIGLIP vision encoder, maybe 400 million parameters, feeding into a Gemma large language model that's about 2.6 billion parameters.
Okay, so that's the perception side. What's the other part?
That's the action expert, the AE. It's much smaller, maybe 300 million parameters. It's also based on a Gemma architecture, but downsized. It's connected to the VLM using a Mr. of Experts setup, and its job is to actually predict the sequence of actions, the motor commands, using something called flow matching.
So VLM understands, AE acts. Got it. And the performance starting point on that 4090 really highlights the pass they faced. Naive PyTorch was over 100 milliseconds.
Yeah, 106.5 meters for 2 views, just running the standard code.
Even the optimized JAX version from OpenPI was still 53.7 meters.
Still way too slow for that 30 hertz target.
And they got it to 27.3 meters. That's like a 4x speed up from the naive version. Let's break down how they did it. Phase 1 was about tackling the low-hanging fruit, right? The overheads.
Pretty much. When you first run a complex model like this in PyTorch, the surprising thing is often how much time is spent not doing useful computation on the GPU.
What do you mean?
It's the CPU. The Python code itself launching thousands of tiny CUDA kernels, these little GPU operations, for every single inference step. Each launch has overhead, communication between CPU and GPU driver. It adds up massively.
Okay, so how do you stop the CPU from micromanaging the GPU?
The key tool here is the CUDA graphs. Since the transformer architecture is very predictable, it doesn't have lots of if this, then that branches that change the computation path. You can basically record the entire sequence of GPU operations once.
The macro.
Sort of, yeah. You record the stream of kernels, then you can tell the GPU driver just replay this exact sequence. It does autonomously, entirely on the GPU side,
Right.
bypassing Python and the CPU overhead for every step.
And that alone gave a big boost.
Oh, yeah. Roughly a 2x speedup just from eliminating that CPU bottleneck. That was the first major win.
Okay, CPU overhead tackled. What was next in phase one? Simplifying the actual computations.
Right. Simplifying the computational graph. Think of it like optimizing code, but for the GPU operations. Combining steps, pre-calculating things. It's often called fusion.
Like the RMS norm fusion you mentioned.
Exactly. RMS norm is a common layer in transformers. It involves some calculations and then applying scaling and shifting. They mathematically folded those scaling and shifting parameters directly into the weight matrix of the next linear layer.
So instead of norm linear layer, the norm math gets baked into the linear layer itself.
Precisely. Fewer operations, less data movement. Another clever one was action time encoder folding. This was specific to the action expert. Part of the AE involves encoding the current time step. Since there were only 10 possible time steps in their setup, they could pre-calculate the results of a linear layer for each of those 10 steps.
Ah, like a lookup table.
Kind of. They essentially pre-computed those results and fused them into the bias vector of the following layer, just before the SILU activation. Again, fewer operations, fewer amass, multiply, accumulate, counts.
Smart. And then there's the classic QKV fusion, right? Standard transformer optimization.
Absolutely essential. Instead of 3 separate matrix multiplies for query, key, and value, you stack their weight matrices together into one big matrix. Do one large matrix multiplication, then slice the result back into Q, K, and V.
More efficient use of the GPU cores.
Exactly. And they didn't stop there. They also fused the rotary positional encoding, the ROP operation, directly into that big matrix multiply and pre-computed some weights. All these graph simplification tricks together saved another maybe 7 to 8 milliseconds.
It's clear they were squeezing every bit of performance. But it wasn't just the GPU, right? You need the whole system to be fast. What about getting the images in? Things like that.
Good point. An end-to-end system needs optimization everywhere. Image resizing, for instance, can be a surprising bottleneck on the CPU. They wrote custom code for it and made sure the camera's output resolution was already close to the 224 by 224 the model needed. That got CPU image preprocessing down to under 60 microseconds. Tiny.
Wow.
They also use techniques like pinned memory for faster CPU-GPU data transfers and static buffers to minimize jitter, that variability in execution time that can really mess up a real-time loop.
Okay, so phase one, cleaned up the overhead, streamlined the graph, got the data flowing fast. That got them closer, but not quite to the 27.3 meters target. Phase two sounds like the real deep dive into kernel optimization.
Yeah, this is where things get intense. Even after simplification, the graph still had something like 24 GMM-like operations matrix multiplications or similar. And the standard library kernels, like kubeless or cutless, aren't always perfect for the specific matrix sizes you find in these models.
They're too generic.
Sometimes, yeah. The tiling strategies, how the work is divided among the GPU cores, might not be optimal for, say, a weirdly shaped matrix in the Vision encoder. So they manually tuned these using Triton.
Triton lets you write custom GPU kernels more easily.
Relatively easily, yes. It gives you more control than just calling a library function. By tuning the tile parameters for their specific matrix dimensions, they squeezed out another 1.5 milliseconds or so.
And that little detail about the LLM running 17 times instead of 18, that really shows the level they were operating at.
Doesn't it? They realized the VLM just needs to pass its key value cache, its memory, to the action expert. The final output features of the very last transformer layer in the VLM weren't actually needed downstream.
So they just chopped it off.
Yep, saved about 0.7 milliseconds. It all adds up. Then they looked at the feed-forward network, the FFN, inside the transformer blocks. There's usually a gated linear layer structure there.
2 parallel matrix multiplies, right?
Right. One feeds into an activation like GELU, the other acts as a gate, and they get multiplied together. They figured out how to fuse those 2 parallel matrix multiplies. By doing that, they could coalesce the memory loads and stores, basically reading the input data once for both operations, improving how well the data stayed in the fast caches. That saved another 1.7 milliseconds.
Hey, these are getting quite technical. What about this partial split K thing? It sounded interesting even if the game was small.
Yeah, that was a neat case study. They found one specific GEM operation, dimension $512 times 1152 times 1152. That was just awkward to distribute evenly across the 128 streaming multiprocessors, the SMs, on the 4090. using standard tile sizes like $64 times $64.
Some SMs would be idle or less busy.
Exactly. So they split the K dimension, the middle one, into two uneven parts, 10, 24, and 128. The big 124 chunk could then be tiled perfectly, using 64 times to 64 Faria tiles across all the SMs. The smaller 128 chunk was handled separately.
Maximizing hardware utilization even for a tiny gain.
Right. The actual time saved was less than 0.1 milliseconds, but it shows the depth of the optimization. It's about making sure every part of the silicon is working as hard as possible.
And the final bit of kernel tuning was fusing scalar ops.
Yeah, the sort of cleanup fusions, things like adding the bias, adding the residual connection, applying the activation function. They fuse those directly into the main matrix multiplication kernel's accumulation phase. And for RMS norm, instead of calculating the norm and dividing immediately, they computed the necessary statistics per token and then performed the division step within the next GEMM kernel. Reduces memory traffic again.
And that accounted for the last few milliseconds.
Roughly, yeah. That brought the remaining gain, maybe around 4 milliseconds or so.
Okay, so after all that intense engineering, CUDA graphs, graph simplification, deep kernel tuning, they land at 27.3 milliseconds. The next obvious question is, how good is that? Is it near the physical limit?
That's where the roofline model comes in. It helps you estimate the theoretical best possible time, given the hardware's limits.
Which are mainly memory bandwidth and compute power.
Exactly. For the RTX 4090, you look at its HBM bandwidth, how fast it can move data, about 1 terabyte per second, and its tensor core compute throughput, how many calculations it can do, about 91 teramax per second for BF16 precision. Based on the number of operations and the amount of data the serial model needs to move, the calculated roofline, the absolute minimum time for 2 views was 19.7 milliseconds.
19.7 meters, so 27.3 meters is still a bit off from that theoretical perfection.
Right.
What accounts for the gap?
Well, the roofline model assumes perfect conditions. One major real-world factor is synchronization overhead. You have almost 1,400 matrix multiplications in this model. Even with CUD graphs, launching the next kernel sometimes requires waiting for the previous one to finish writing its results consistently, making sure all the SMs are seeing the same data.
The standard CUDA graph still had some overhead.
They measured it at 1.72 milliseconds. Not huge, but it's there. So they went even further and implemented a custom software barrier using global memory. It's a trickier way to synchronize, but it cut that overhead down to just 0.86 milliseconds.
Okay, so if we add that minimal synchronization overhead to the theoretical roofline,
you get $19.07 TexMS plus 0.86 TexMNS, which is $20.06. That's arguably the more realistic lower bound for this model on this hardware.
which means their achieved 27.3 meters is within about 30% of the absolute best case scenario. That's incredibly efficient for such a complex model.
It really is. It shows they squeezed almost everything possible out of that GPU.
But like you said earlier, the numbers are great, but the real test is performance. The falling pen experiment.
Right. The proof is in the catching. It was a tough setup. A 30 FPS camera, which already has about a 2-frame or 66 meters, inherent delay just from image capture and transfer.
Plus the robot's physical limits.
Yeah, the grippers themselves took 60 milliseconds to close, and the pen falls about 30 centimeters pretty quickly. The training data they collected showed you needed the entire system delay, perception, inference, action to be under 200 milliseconds to reliably catch it.
And the result with the optimized VLA.
10 out of 10 successful catches, 100%.
That's the validation then. It proves this highly optimized billion-parameter model can operate reliably within the tight constraints of a dynamic real-world task. It matches or maybe beats human reaction times in that specific setup.
Absolutely. It makes real-time control with large VLAs a present-day reality, not just a future hope.
Okay, so they hit their 30 hertz goal, proved it works. But then the paper introduces this really cool concept, the full streaming inference framework, pushing beyond 30 hertz towards 480 hertz. What's the idea there?
This came from an interesting observation about the VLM and the AE components. They realized the action expert kernel, the smaller part doing the action prediction, was mostly limited by memory bandwidth, how fast it could read and write data, I/O bound.
Okay.
Whereas the big VLM kernel doing the vision and language processing was limited by raw compute power. Compute bound.
Different bottlenecks for different parts of the model.
Exactly. And when you have different bottlenecks, you could often overlap the work. They measured it. Running the VLM once plus 10 AE steps sequentially took the full 27.3 milliseconds. But running the VLM on one CUDA stream while running the AE steps concurrently on another stream took only 26.3 milliseconds.
So the AE work could happen partially during the VLM work.
Pretty much. Because the VLM was busy crunching numbers on the tensor cores, The memory bus was relatively free for the AE to do its data shuffling. This concurrency showed they could theoretically run 30 VLM updates per second and 480 AE updates per second on the same GPU.
That insight leads to this hierarchical control structure they propose, right? 3 loops running at different speeds.
Yeah, this is maybe the most forward-looking part of the paper. They envision restructuring the whole control system based on these different frequencies, almost like biological reflexes versus conscious thought.
So what's the fastest loop?
The force loop, running at 480 hertz. This is for ultra-fast feedback. Think inputs like force torque sensors on the robot's wrist, or motor currents. These signals can update the action expert directly every couple of milliseconds. But this required a change. They had to modify the AE's prediction method, the flow matching, to allow it to decode action chunks gradually, autoregressively, influenced by this high-frequency feedback, rather than predicting the whole action sequence at once based only on the VLM input. It's like fine-tuning the muscle commands on the fly.
Okay, that's the super fast reflex. What's the middle layer?
That's the visual loop, running at the 30 hertz we achieved. This is the VLM, processing the camera frames, understanding the scene, figuring out the high-level goal, and then providing the updated context, the KV cache, for the action expert to use as its baseline.
So VLM provides the what and where. AE refines the how very quickly using force feedback.
Kind of, yeah. And then there's the slowest loop, the textual loop.
For language commands or reasoning.
Exactly. This runs at about 30 tokens per second. And the clever part is it's almost free computationally.
How so?
Because when the VLM runs its transformer layers to process the image tokens at 30 hertz, the necessary weights are already loaded into the GPU's memory and caches. So they can immediately reuse those loaded weights to compute the next token for the language part, piggybacking the text generation onto the image encoding pass.
That's really efficient. So you get background reasoning or instruction following without hurting the visual latency.
Right. Gives you this multi-layered control system. Fast physical reflexes, medium speed visual perception and grounding, and slower background reasoning, all running concurrently within the same optimized VLA structure.
It really does feel like a different way to think about robot control with these big models. Okay, looking forward, what do the authors see as the next big challenges or directions? How do we go even faster?
Well, hitting 60 FPS or even 120 FPS for the visual loop is the next obvious target.
Yeah.
That's tough because the vision side is compute bound.
Need more maxis per second.
Yeah. So the most promising direction there is probably pushing lower precision. Getting 8-bit quantization working reliably for these large VLAs could potentially double the throughput. That's a big research area.
What about handling more cameras without slowing down?
That's the other angle, adaptive view selection. Instead of blindly processing pixels from, say, 4 cameras all the time, maybe the model could learn to dynamically focus on or fuse information from just the most relevant views for the current task step. Fewer tokens to process means faster inference.
Makes sense. And scaling up the models themselves, they optimized a 3B parameter model. What about 7B or larger?
They think scaling to 7B should be feasible, especially looking at upcoming hardware like the RTX 5090. Projections suggest the big jump in the 50 series might be more in memory bandwidth than raw compute power, proportionally.
And since the action expert was bandwidth limited.
Exactly. More bandwidth should help scale the AE part quite effectively. Scaling the compute-bound VLM might still require those precision tricks, though.
And the final future direction they mention is even more fine-grained feedback.
Yeah, the idea of making individual layers within the action expert somehow aware of the very latest sensor signals, potentially pushing that control frequency even higher than 480 hertz. That's more speculative, but interesting.
It really feels like this work opens up a new chapter, integrating that super fast 480 hertz force loop with the 30 hertz visual perception loop. It suggests a control paradigm much closer to biology, with different processes running on totally different timescales. Which leads to a final thought, maybe for you listening. If robots can operate with both fast reflexes and slower perception reasoning like this, how does that change how we should train these models? Do we need to move beyond training them on simple single time step predictions and start thinking about training these distinct asynchronous control loops directly? How do you design tasks for that?
That's a deep question, and likely where a lot of research will head next. For anyone wanting to dive into the code and see the low-level optimizations discussed today, the authors made it available.
Right. Where can people find that?
It's on GitHub at Dexmal, DEXMAL/realtimevolva.
Perfect. Well, this paper is a fantastic example that these massive VLA models aren't just theoretical possibilities for the future. With some serious, dedicated low-level optimization, they can be practical, real-time tools for robotics right now.
It really bridges that gap between large model capabilities and real-world robotic speed requirements. Exciting stuff.